Hello everyone. Today we're looking at the problem maximum number of distinct elements after operations, which was question 2 in weekly contest 429. So the question reads that we're given an integer array, nums, and an integer k, and we're allowed to perform the following operation on each element in the array at most one time. So basically we could take any element in the array and we can add an integer in the range from -k to k to that element. And our goal is to maximize the number of distinct elements in nums after performing those operations. So pretty simple problem statement, but you see there's a bit of a trick that we need to do in order to figure this out. So the example given is 1, 2, 2, 3, 3, 4 as our array, and k is 2, and we're going to output 6. And we do that because after performing these operations, we can change nums to -1, 0, 1, 2, 3, 4, and we have 6 distinct elements in that array. So we return the number 6. So we're going to look at a slightly different example, but I think it demonstrates well how this problem works. So your initial thought might be, well, what if we just look at each element in the array and try to find a number maybe in that range that hasn't been used yet. So for example, if we have 4, we can go all the way down to 2 here, or all the way up to 6. And what we could do is say, maybe let's look at 4, let's iterate through this range 2 to 6, and try to find an element that's not used. So for example, in this first case, we'll say, okay, 2 is not used, so maybe we can mark that down and say, we've taken this 4, converted it to a 2. Then maybe we can go to the next one, right, and say, okay, let's do the same thing here. So we'll go from 2 to 6. We'll see 2 has already been used, so we can go over to 3. We'll say, all right, 3 hasn't been used, so we can add that. So you see, we're kind of brute forcing it, but you might notice a bit of a problem with this. So this means for each element, and you'll see we have 10 to the 5 elements in here, we have to go through potentially 10 to the 9 elements. So this essentially is greater than n squared, right? So this is not going to be efficient. We can't just brute force it and check every single operation or every single way that we could do this, but we could kind of use this idea and try to be smart about the numbers that we're checking. So what does that look like? So let's say I do the same thing. I'm going to start on this first 4, and I'm going to say this 4 can go from 2 to 6, right? And I am going to check all these numbers. So I'm going to say, okay, well here, I can make this 4 into a 2. I have my set. This 2 hasn't been used yet, so let's add it in. So now we're going to move to our second element. So what are we going to do to avoid all these computations, right? Well, I'll know that I already have a 2, right? So is there any point in starting over at 2? Like the range I can go to technically is from 2 to 6, right? But why would I do that? Because I know that this element's used, so really I should start from 1 above this, right? So I could say, all right, well, instead of starting at 2, I could maybe start at 3. So if the second 4, I can start from 3 and go to 6 and say, okay, which of these numbers hasn't been used? So then I could see 3 hasn't been used, and I could add that to my set. So kind of the idea here is that we are going to go through our elements, but we want to keep track of the minimum value that has been used, right? So we'll see when we start here, there's no value that's actually used yet. We have a completely empty slate. So you can go through this range and say, all right, 2 hasn't been used, so let's add that into our set. But then going forward, we want to be smart about what we're doing. We don't want to check 2 again because we know that is already taken. So let's kind of use that previous value in order to shrink the range that we're looking at. So here we're not looking over k, but we're actually looking over k minus 1 values, right? So you see that we're actually going to be able to shrink our k every time we go to a new element. So another important point here is we have to make sure that this array is sorted, right? And I picked this example specifically because sorting has no impact here, but I also want to look at exactly what you would have to do for an unsorted case. So let's say we had this example, 4, 3, 2, 1, and our k equals 2. Well, what do we do here? So we can go for our 4, as we know, from 2 all the way to 6, right? So that's our range here. So if we process this number first, we're going to look over this entire range. But then we come to 3. So what happens here? We can go from 1 up into 5. But you'll see that we already checked all the numbers from 2 to 6. So because this is out of order, right, we're basically checking everything from 2 up until 5 again here. So you'll see that if this is out of order, we're going to end up doing a lot of repeated work. So let's try to sort this. So if you go to 1, 2, 3, 4, let's see what happens. And let's cross this out just to not be confused. So here we can go from -1 to 3, right? So what we would end up doing is we'd say, okay, well, here I immediately found a number that I can adjust this to. So I'm going to use this. So we're going to end early and not even check 0, 1, or 2, right? These are not going to get checked because I already found an element that I can assign this to. So now what we're going to do is go over to 2. Well, I know I can go from 0 up until 4 here, right? And you'll see that previously I'm starting at 0 now, but I didn't actually check this last time. So now I can go from 0, 1, 2, 3, 4. I'm going to see that my 0 here is not used, so I'm just going to use this one and not check these. The next time I'm going to go to 3, and I can go from 1 up until 5. So you kind of see a pattern here, right? We're actually only checking each number one time. And this is why the sorting is so important, because it allows us to find the smallest number, not check these, and then the next time we can be smart about which numbers we're looking at and say, I know what I've already seen, and I actually haven't checked these numbers yet. So really what I'm doing is I'm checking each value only one time. And this is why sorting is really important here. So now I want to do a dry run of this specific example so you can see exactly how we're going to use all these ideas together. So we're going to have a couple things to start. We're going to keep track of our minimum, right? And what this is basically is this is the boundary for what we want to check. So say, for example, we previously put an element at the value 2, right? Technically, what if our k is 10,000? We could maybe go all the way from like negative 10,000 to 10,000. But using this min, we could say, all right, well, I placed something at 2 previously, so I don't want to go any lower than that. So this min kind of allows us to keep track of the last element that we used to assign a value to, and we can shrink the range that we're checking using this. Total is going to be our answer, and you'll see that I started it at 4. So the way this works is that we're going to assume that all of our numbers can be distinct until proven otherwise. And when we see that they cannot be distinct anymore, what we're going to do is subtract 1 from this value. Then we just have our used set, and this is where we're going to keep track of any value that we have used and basically converted our numbers to. So we're going to start at 4. And we know here that for our first one, we can go from 3 to 5, right? So now what we're going to do is say, okay, so let's iterate through this range. So what I'm going to do is say, is 3 in my used set? It is not. So what I'm going to do is I'm going to add it in here and keep track. And here I don't decrement this because I've found a number that I can convert this to. So now what I do is say, all right, I previously have used a 3, right? So what I want to do is say my minimum now is going to become a 4. So why does my minimum become 4? Because I previously used a 3, right? So for my next number, when I start searching for a number that I can convert it to, I want to actually have my lower bound be 4, because I know that there's no point in searching 3 because I've already used that. So this is a way that we're going to shrink our search space by keeping track of our min. So now we head to the next 4, and let's see what we're going to do here. So we could do from 3 to 5, but remember, we're keeping track of our minimum here, and this is going to help us shrink the number of elements we have to check. So really what we're going to do is say, we're going to make this 4, because we've already used a 3, and we know that the minimum value we want to start looking at is our 4. So now we can search from 4 to 5 and say, okay, well, is 4 used? Well, it is not, so I'm going to add it here. So same thing. But now what I want to do is update my minimum to be 5. So now my minimum is 5 because I saw a 4 previously. So now the smallest value that I want to start checking is 5. So now I'm going to go to my next 4. So here what I want to check is a range from 5 to 5. So this is coming from my min value, and this is the value of 4 plus k. So now I want to check, is 5 used? Well, it is not. So what I could do is basically put this here, and then what I would do is update my minimum to be 6. So now my minimum is 6. So this is where it gets interesting. I'm going to move to my last 4, and basically what happens now is I'm going to say, okay, so for this 4, I can go from 6 to 5. But you see, this is not a valid range, right? Basically, we could search this range, but it's kind of an undefined or, a weird operation to kind of go from a larger to a smaller. So we don't really want to do anything here. And you'll find that there's no numbers in this range that we can assign to. So in this case, we come to our total and we're going to decrement it by 1 to 3, because we see that by the time we get to this 4, there's really no values that we can assign to given our k and what we've used previously. So here we're just going to decrement. Then at the end, we've gone through all these elements. So we're going to return this total here, which is 3. So what's the time complexity of this algorithm? Well, the limiting factor here is the sorting. So we have to sort the algorithm. So that's going to be a n log n time. We could also think about the actual operation we're doing. So we're going through all the n elements, and we're basically going through each k value at most one time. So we could also say this is n log n plus k, but with big O time complexity analysis, we're just going to keep this larger element for simplicity and say that our algorithm is n log n. So let's hop over to the code and see exactly how this works. So we have to do a couple things to actually get our algorithm set up. So we're going to have this set called used values, which just kind of keeps track of the values that we've already used. We're then going to sort our nums and have two variables mini, which kind of keeps track of the lower bounds, which is just set to negative infinity to start. Then also our total, which is going to be our answer. And we're going to start this with the length of nums, because we're going to assume that every element can become distinct until proven otherwise. So what we're going to do is we're going to go through all the numbers and nums, and we're going to assume that it's going to be not unique. We're going to have this flag set to false. Then what we're going to do is we're going to iterate through the range from the max of num minus k, or mini, to num plus k plus 1. So what's this actually doing? So this num minus k is basically going to be, in the case that, say we started fresh in our algorithm, this is going to be whatever number we're at minus that k. But if our minimum value is greater than that, then we don't want to start searching here. We want to start searching here, right? So this is basically a way of saying either start searching at num minus k, or if the minimum boundary is greater than that, then we want to search here. Then we want to end at num plus k plus 1. So we want to go all the way up to num plus k. In Python, this is a non-exclusive range, so we have to add plus 1. So then what we're going to do is for each number, we're going to check and say, if that value has not been used yet, then we can say, all right, we have found a value we can use. We're going to add that to our used values, and then we're going to update our minimum to be either the maximum of what we already have or I plus 1. So this would be saying we just used 4, for example. We want to say our new minimum will be 5. So we don't want to search for it again because it's already been used. And here what we do is we're going to break out of this loop because we've already found a value and there's no point in going through more values and looking for another one. Then when we get here, if we have not found a value that we can use, we're going to subtract 1 from our total. And finally, we just are going to return our total at the end. So let's submit and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.